Hey everyone, if we can settle in. I'm going to make a meal of this one, I know. This afternoon we have Tennessee Leeuwenburg, who works for the Centre for Australian Weather and Climate Research with a small team of developers working on advanced weather forecasting software. However, in his spare time, he dabbles with artificial intelligence and robotics, which is the topic of the talk today, in which he'll be demonstrating Python-driven robot cars in the Open Race Car Simulator. So if we can get a warm welcome for Tennessee Leeuwenburg.
All right, hello and thank you very much. I haven't done a 45-minute before, so I've just assumed the same amount of time per slide and we'll see how it goes. So, a bit of introduction to myself has essentially all been said, but I will introduce how it is that I got interested in robotics, because that's the point of interest here. Is that as an intellectual play space, I cannot think of anything more just fundamentally awesome than robotics. And really, that was basically the whole justification for submitting this talk, and the entire time between then and now has been creating the content for the talk to meet the impending deadline of doom. So we'll see how far I got with that, but I would just mainly want to share my enthusiasm and interest for getting into an area like this as something that's incredibly satisfying. So I did a carefully researched and fact-checked exercise of going to Wikipedia to look about real car racing, because I thought I'd introduce the talk with real racing and then follow it through with the robotic racing. So the first car race was held on April 28th, 1887, and it had one entrant who won. So much like myself today. So there's a few facts there. Modern racing, the kind you see on the television with fast cars and loud noises, has a Wikipedia entry. It says there's 11 different categories of modern competitive racing, and not one of them is a robotic competition, which is a tragedy. So, boo. So I'd really like to see where some of this stuff could go, because I'll be talking about some of the real robotic car attempts that have been created, and then it just seems like such a gap that we don't have the Formula One of robotic cars. So robotic vehicles in general, I don't know how much the audience may be familiar with, but you get, the remote control car you played with as a kid, thing called micro mice. I'm not sure what the plural is, but essentially very small vehicles that do a limited amount of things, essentially algorithms for going through mazes or very small things, and the emphasis there is something you can do at home. You can use your phone to run a robotic car, mount it in a little chassis. Then there are more major traditional sized cars, self-driving cars. So Google famously have a self-driving car. Many of the other car manufacturers now have self-driving models that they have under R&D. Audi famously did an ascent of Pikes Peak. And if you haven't ever Googled for quadcopters and quadrotors, just do that now, because it's like, wow. Okay, so here is the most famous robotic car, I would say. So this is a recording of Stanley. So what's happening here is this is the DARPA 2005 Grand Challenge. So obviously I've stolen this video rudely from the internet. All sources fully referenced in my slides, and I hope I haven't done anything wrong. So at no stage had any car completed this race before. What you see there is an array of laser-based rangefinders on the top, known as LiDAR. And this is inside of one day completed the track. The vehicle you see immediately behind it is the official racetrack, and this is an exercise shared, essentially headed by Sebastian Thrun, who is an employee of Google and also a professor at Stanford. So this was a very serious accomplishment in the space of robotic cars. As you can see, it didn't go very fast, and it was essentially operating in a risk-free zone as far as pedestrians were concerned. So the next grand challenge, a couple of years later, was the urban environment. So you can see the cars become a little bit more streamlined. It's got the spinning LiDAR on the top, and the car is capable of observing the traffic in each direction, waiting till it makes a safe point to make its turn, turning in front of other vehicles. And you can see it's doing not a bad job. In a minute, I haven't got my timings exactly perfect, we will see this moving into the visualization of what the simulator on board the vehicle sees when this same sequence of events unfolds. So just here. So what you see here are the highlights of what is visible to the car using its laser-based array, the mechanism by which the car performs its logic. Green represents its intended trajectory. Red represents an obstacle. Blue is obviously the lane markings, and the orange there represents a waypoint. So there's some quite sophisticated hardware that's gone into making this happen. The computer on board from memory is just a kind of high-end desktop equivalent, so it's kind of a, I don't know, like a quad-core 6 gig of RAM, something like that. I looked into it, and it was, you know, impressive, but not out of this world. It was the kind of computing that many of us have access to. Not so much with the $40,000 radar array on the top, though. Kind of, yeah, put me a bit out of my budget. Yeah, not so much on SparkFun or little bit electronics. Now this is not an autonomous car in the same sense of it's more like a remote control car. Doesn't have the array of sensors, but this is just a minute and a half of just pure drop dead awesome, and I just couldn't not include it. So this vehicle is the Traxxas X01 radio control motor car. No sensors, no autonomy, 100 miles per hour. So I compared this with my actual car, a 1997 Subaru Forester, top speed 150 kilometers per hour, 100 miles per hour, for those in the audience who can't do the conversion on the fly, 161 kilometers per hour. This is what robotic car racing should look like. The size and dimensions of it are roughly 70 centimeters long, so it's about that big, about that wide, about that tall, and retails for about $1,000 US. So this is something we can all get into. It is drivable via iPhone, something which is fairly impressive, so you can get the iPhone app for this particular vehicle. But even $1,000 may be cheaper than a $40,000 laser-based radar array, still outside of my budget, unfortunately. So as you can see, we have small and large robotic cars in the world that might exist, that they exist on a spectrum from drive-by wireless, autonomous drive-by-wire. So that's what I call the category of this Traxxas, where obviously the vehicle itself has no driver in it. It's driven remotely. Many people pursue robotic cars through essentially having a radio transmitter from their PC through to the actual vehicle, and they do the AI programming on the computer. They may have, for example, supervised systems where you give it like rough directions, but you might have things like obstacle avoidance or automatic braking built into the AI. And of course, our actual cars increasingly are robotic. So that comes from things where we've had for many, many years, things like ABS, that just happens. You don't do it. It's just, it automatically ignores your instruction to brake at a particular intensity and modulates that intensity based on the wheel skid. Things like reversing sensors, they can inform you, but of course they extend to things like automatic parking, which I have never actually sat through, but I've known people who've had automatic parking cars here in Australia, which frankly sounds pretty convenient to me. Robotic car racing. So this was the extent of what I could find in terms of actual robotic car racing of any great interest. There's the DARPA Grand Challenge, Urban Challenge, the Pikes Peak Ascent, and as I've said, it would be awesome if there were more physical car racing robotic competitions. But there aren't. So here's one you can use at home. So this is open source racing car simulator. It's now forked into something called Speed Dreams for a slightly more modern code base, but essentially it's the same application. And so this looks like any great modern computer game. So with awesome 80s soundtrack to provide for your listening pleasure. but you can see that it includes reasonable vehicle physics, so it has a decent model in terms of each tyre, for example, reasonable road condition simulation, the sensors on the cars in the actual TORCS system have full access to the track information, but where we'll be headed is a layer over the top of this, which is essentially the same as you would see on a Google self-driving car or any other kind of robotic car interface. So I think we've seen enough of the cars driving around the track. Let it wash over us for a while in all of its glory. I'm sure we can all remember our PlayStation 2s and some glow sticks and a few credits. So I just wanted to let the credits roll by to just give the people involved in the production of the software and the video their due credit. Okay, so this is something you can very much do yourself. So simulated racing corresponds extremely well to something you'll find on an actual robotic car. The abstractions are very much the same. So if you had, for example, an Arduino, your own personal chassis, a rangefinder attached to it, you would have the exact same thing that you have over here in the racing car simulator. You may have a few differences, your brakes might be a little different, but other than that you'll pretty much be there. You have distances and rangefinders, speed steering brakes, noisy, sensors are noisy. So in the real world, that's what happens. In fact, they're not just noisy in the real world, they're kind of like, they're terrible in any given state. They can easily go, oh, I'll just measure nothing versus 100%. For no particular reason, for like a second. They'll just kind of vague out and just go for a wander. So I discovered this when I mounted essentially a rangefinder just on a physical object and just went like this with my hand and then put something in front of it, it would very much blip. So handling noise is something that you have to do, and creating noise is something that the simulator will kindly do for you. Have a complex environment, open-ended design and problem definitions. So the rabbit hole for this is infinitely deep. I'm not going to attempt to go all the way down an infinitely deep hole in this particular presentation, you'll be glad to hear. But it does give you an immense amount of room to play and learn. So how does this tie into competitions? So this does have a yearly competition. You can enter this thing. Typically Java or C++. So to date the competition has no Python entries. However, thanks to what someone will see in a little bit, not this guy, they have created now a Python interface for this. So for the first time there is the potential to, at least in the safety of your own home, connect up a Python client to the racing simulator and compete against all of the bots which are downloadable and executable, and you can attempt to race your Python client against their clients. Of course, since I had never written a robotic car before, I did not fare so well, but I have managed to complete, say, a full circuit, and I'll demonstrate some of the algorithms here. And the original work, you can read a lot of the paper, an IEEE paper that introduces it more formally. So this works by essentially modifying the game to provide a pretend bot, which is actually just a socket-based server that will just listen to incoming data on the socket. So you can essentially drive one of the bots in the competition by passing data to a socket that you open, and you read the game state by attaching to the server and sucking data out of it. And this particular individual here went and created the Python version for it, which is just awesome. And it's like super easy to use. Other than installing TORCS, which is now it's like 2008 code, so your operating system may not comply anymore. But it's essentially, it's not really a big deal. So this came about as a result of doing a course called, it's by Udacity, called Programming a Robotic Car. And it's an artificial intelligence course, runs for 7 weeks. And it was the whole company was started by the same guy, Sebastian Thrun, who was talked about earlier in the context of the DARPA challenges, and is a really serious and impressive guy. And he has decided to create an alternative education platform online called Udacity. And you can do a completely free artificial intelligence, totally creditable, well, not creditable in the sense of you can't actually get credit for it. I mean, it's credit-worthy course in artificial intelligence. In this case, clustered around programming a robotic car, which is what provided the inspiration to, I suppose you'd call that Mr. Langquarden, and also to myself. I didn't write it, I'm just saying we were in the same course. So getting to know your vehicle, what does a robotic car look like? You have basically 20 laser rangefinders that are virtual so that you can look around. You can get your current angle to the center line of the track as a sensor reading. Cross-track error, which is just like the amount of meters that you are to one side or the other of the particular track. Knowledge of distance to competitors, if you have any. And you drive with an accelerator, a brake, a steering wheel, and the clutch. Unfortunately, the clutch isn't hard to use. You don't kind of, do that or anything. You just send it an integer and it switches. So, fortunately, that's not too bad. So, sorry? There is a gear change, yeah. So you send the integer to the gear change and you take off the accelerator momentarily or something. I don't know. The software does it. It's provided as an API, so it's not a problem. So I'll jump forward to the next slide and then back to this one. This picture, which we probably all saw back in year 11 and some of us may have never seen since, will be your friend. It's an incredibly helpful picture when it comes to trying to figure out what's going on in this diagram and how you can drive a car. So this is a visualization of a car driving at 90 kilometers per hour using nothing but these 20 pieces of information. And so that's essentially the distance to the track edge at any given situation, and it's making the turns appropriately based on that input data, and that's where it hit a wall. So not quite so perfect in that particular example. There were a few kinks to work out in that particular issue, and that's where we come back to this particular image here. So if you remember in your head, there were lots of lines sticking out, and they may essentially stick out to over here somewhere, and essentially you normalize that, bring that down to here, and then all of a sudden all of these functions that you might have used or vaguely remembered, you can bring back to reality, and you go, oh, okay, I want the y-axis of that thing. What's the y-axis of this thing out here? Well, it's the y-axis of this thing here. Oh, that's the sine of that particular function times that distance. And like, it's not so bad when you just like sit down with a, like this picture and a pencil and like draw it out. All of a sudden it kind of makes sense, even though like I would never call myself a really particular competent geometrician, math guy. But overlay that picture and you'll sort of sort yourself out. And the one good thing is mostly you get it right once and it just works. Because generally if you get it wrong, everything just explodes straight away and you can't make any progress. It's a fairly binary success relationship here. So what we need to do is let's go and relate that to what we just saw about driving around. So essentially, so what you can see here is me stuffing around with the command prompt. This is me loading up TORCS in single race car mode, firing up my my bot on the right there that's doing the driving and also running the GUI. And you can see driving around the racetrack, coming up straight. There's a little bump. You can start to see the edges appearing in the image over on the right. Driving around. You get it. So that car there on the left is driving on the basis of the input data over on the right. Mostly what it's using is this thing called current angle to the middle of the track. So what you'll see here is that it fails to take the edge. It just drives mindlessly, in big grandpa swings all the way through the track, kind of like me on my L's. But it does very much get there. So and that steering algorithm was a one-liner provided by someone else, which I'm very grateful for, because doing better suddenly gets really, really hard. So all of a sudden you need to have a map of where you are, you need to have an intention to actually follow a specific path, whereas this is just a real simple response to a single input function that provides the angle to the steering wheel. So there we go, slowly completing a lap of the track. So where do we go from there? Basic algorithms. Steering, braking, obstacle avoidance, if you must, and strategy. So I didn't even dare touch strategy. So I will dive a little bit into just some of these algorithms. So one of the things I desperately wanted to do for this course was just make it the most incredible lights and successful sort of, you know, exploration of cars just fanging around corners. But I didn't really get there because it was a bit hard, to be really honest. And getting into a serious competition like this with so few inputs, you really need to you kind of need to pull out that textbook, unfortunately. So I'm going to dive a bit into how we go about doing some aspect of localization and mapping, just to give you a taste for the kinds of algorithms that you would need to do when building this kind of car. So that's the one-liner, by the way, for the steering algorithm that was just provided, which is where you take the angle to the track, and then the distance that you're off, which I realise they're different units, but somehow this works anyway, because I think generally the errors don't get too large. And steer lock is you can only turn 90 degrees on your steering wheel. And that will take you around the track. To go further, what you need is a motion model. You need to know how your car is going to respond to steering in a more intelligent kind of way. Partly we need this because there's no compass, so you have absolutely no idea what direction your car is facing at any given point in time. You can in fact work out whether you're going away or towards the starting line, that is provided, but you have no sense of north-south, I've just turned to the left, I've just turned to the right. All you know is what's happening to the track edges around you. So without being able to model your expected trajectory, you can't actually plan where you want to go. So here we go. So this attractive hand-drawn image was stolen from the Udacity course site, for example. And you can see there that this is implementing a so-called bicycle model. So ignoring the differences between the course taken by the inner wheel versus the outer wheel, and just imagining that it essentially had one track of motion. So just a few of the basic definitions. So the amount of steering you're applying is alpha, the amount of angle that you already have, your compass direction is theta, the distance of the car and the length of the car and the distance you're travelling in a given time slice. So TORCS will provide you with an update every 0.02 seconds, every 200ths of a second. So in order to respond to what's going on in TORCS when you're building your AI, you have to be able to provide it with an update every 200ths of a second. Otherwise what happens is that it will just go with the last known instruction, which may or may not be valid at that particular point in time. So here's a little bit more of the evil maths that will drive your car around the circle for you. So this is also the basis, as I understand it, of steering in modern cars. Because if you have a car and you steer to the left, if you translate both wheels the exact same number of degrees, you'll end up with a car where, theoretically anyway, the inside wheels are not following rotating around the same circle as the outside wheels. And you would need to, for example, rotate. Suppose I'm turning right, that's me turning right. Wait, that's me turning right. And this wheel, okay, now I'm turning your right, and this wheel here has to go further than this wheel here. So either you will tear off your outside wheel and send it spinning away, or you actually need to change the angle of these wheels so that they're rotating around the common inside point. And that's what this thing's doing in the bicycle model sense. It's an approximation of the curve that is locating that inside point that you're turning right around, and then deriving your expected location after some period in time for some given quantity of steering that you're applying to the model. So, some maths later, what we do is we have some code. That's it. It's pretty straightforward code. It's not very many lines long. The first part of the if statement is just catching a divide by zero error, where if you are not in fact turning at all, the location of the theoretical point around which you are rotating is infinitely far away, which is very, very bad. So you handle that, otherwise you're just rotating around a curve. So that diagram from before, yes, very important. So what do we do with all of this? Well, I find it very hard to connect to what's going on without something visual happening. Just kind of, I don't know, in my head, nothing happens until I see a picture. So let's draw a map, right? Drawing a map is really hard if you don't know your starting location, you don't have your initial coordinates, you don't know where you're turning, and you don't know how much you've turned by. So how do you go with that? Well, let's just assume we know where the car is. Step one. let's assume there are no noisy sensors, and every time I turn, the car moves by the exact proportional amount. That means no skidding, no errors in the sensors, no anything, but it's a way. So here is mapping version 1 plus a musical expression of my emotions when something goes wrong. So what you can see here is on the right, I've taken those sensor lines and I've just left them on the graph. And I'm just now drawing the complete plot of what's going on there. And you can see that up on the left there, oh no, oh no, oh no. So that's the experience you will have when programming a robotic car many, many, many times. So then it took me a day to fix that. So this one here is mapping that. No, the video is non-present. Okay, just, I will find. I opened the wrong version of my PowerPoint. Here is the correct version of my PowerPoint. There's Benny Hill. There's mapping that works. So here's rebuilding this in a way that works. So once again, I'm just stuffing around, and this time what I've done is modify my algorithm so that I'm just plotting pixels on a NumPy array and updating that. So what went wrong in the last video was essentially that tkinter, the awesome graphic library that's included with Python by default, was taking too long because of the build-up of objects, because it kept every single one of these line plots, at least so I think. This certainly did in the end fix it. And you can see now I'm just plotting the endpoints as pixels in a NumPy array. And what we'll see here is that the map slowly begins to build itself up. There's a few things of interest to note. One is that despite being on a straight race course, these lines down here on the right where it started are not quite straight. It seems to be going a little far round to the right. That doesn't seem quite right either. But what we'll notice is that that will, in fact, even itself out in a little bit. So one of the things there is that this is going to turn out not to matter very much, because it is rotated, but by the time it does a complete circuit, we'll notice that it is in fact internally coherent, even though it's not quite right. First of all, there's the fact that it's obviously 90 degrees out, just because I got my rows and columns wrong in the NumPy array. But the car doesn't care. It might as well be driving on this particular circuit. And you can see that this is where we can now build up things like planning, localization, calculation of where the car is on its track. Now you can get into these algorithms. You can use these things for taking a finer curve. Obviously, I've chosen now just a simple circular or oval racetrack. The advantage of that is it lets you see what happens when you drive through all the quadrants of the unit circle. So quite often what you'll find is that something that in the normal first 90 degrees will be, say, a positive number between 0 and 1, will flip to be a negative number between 0 and 1 as it completes its circuit, etc., etc. So there will be a lot of bugs that come from just driving a full circuit again and again and again. So here we go, and you see now it's on its final rotation now. It's matching up with its previous location, but it appears to have a different point that it's mapping there on its sensors. Now I haven't got to the bottom of this one yet, so I've got some hypotheses like maybe the bicycle model's just wrong enough that this is what happens, and you can see it's not plotting the exact same course. So I haven't turned on noisy sensors. This is with noise-free sensors. There's no particular reason that any of this should be in any way wrong. I might be driving fast enough that there's some skid in the wheels, so that my algorithm doesn't know its location has changed, but maybe the car's swung and rotated either more or less than has been calculated, and as a result, there's some errors in it. But this is essentially mapping that works. So where do we go from there? So localization, that's the opposite of mapping. So what happened there was I just assumed that every single point in my trajectory was perfect, and that my estimation and my forecast of my location was correct enough, I could just take the sensor information, instead of using it to plot the location of my car, I'd use it to plot the world around me. Localization is the application in reverse of that same principle, where you assume that you have that map that we had before, and you move around and you go, well, every sensor information is still perfect, but now it gives me reference points that I can trust or believe or rely upon in order to place myself within that environment. So you estimate it, challenge your assumptions. And then simultaneous localization and mapping is where you essentially do a more probabilistic correlation of the one to another. And that is where you can get into relating the two and getting into some more serious stuff in terms of planning. That's an example of what I've been talking about there is what I would call global planning. It's not truly global, but the idea is that you have a map of the whole environment and you're trying to locate yourself at a specific point. Local planning is like, oh my God, there's a wall, for example. So that's what I do when I slam on the brakes when I haven't been paying enough attention to the red light in front of me, or the accelerator when I have been paying just enough attention to the red light in front of me and I can just kind of zip through. So local planning is like an instinct layer, global planning is like strategy. So an example of local planning is implementing automatic braking. So this is a simple one with some magic numbers in it, but essentially this is doing, well, what's the diameter of my wheel, what's my RPMs, what's some number representing the point at which my wheels skid. Okay, I'm going to refuse to allow the car to apply any more braking than would exceed my skid threshold. So you always know that you can just slam the virtual brakes on as hard as you want, push it through ABS, and the car will perform the maximum efficiency braking. Now I realise I'm heading towards the end of my time. I do just want to talk about this concept of filtering, because that's a key concept. And that's where you push through more than one virtual car at a time. And so you might take that map that we had before and you might say, well, there's some probability I'm here, but I know my sensors are wrong, so I might be here or on this other location. And you track multiple of them. And then every now and then you'll pass through the start line where you began at 0, 0. So all of a sudden, even though you only have a non-absolute reference point, you just have your relative reference point, which is where you started, every now and then you know where you are at where you started, and you know which of your projections about your map correspond to ending up where you started. And you can start to do these mapping runs and do multiple runs and take multiple spreads of information and probabilities and relate them to how you move through the space. And those kinds of algorithms are covered in these courses. They're extremely exciting, and you'll find you can apply them to other areas as well, but nothing's really quite as cool as cars. So, why would you? So I hope I've given you some kind of presentation. 45 minutes is just not enough to explain all this stuff. It's just not enough to convey just how awesome and cool it is to actually sit down and work on this stuff. And you'll just have to take my word for it. One of the things that I'd love to do at some point is take this and bring this back into an embodied environment. That's what it means when you take the code and place it in something that has a physical abstraction, like a small Arduino bot or cell bot. So that would be cool. So what's next? Hey, anyone want to enter the competition with me? There's I'm sure there'd be space for a Python entry, or at the very least, because this can be played multiplayer, you could probably enter your own bots against your own friends who are racing as people as well, and hey, that'd be quite a kick. So I'm going to wind myself up with just this list of further resources that anyone can get into if they want to go take a look, take it further. Does anyone have any feedback or questions, I guess? Sure. I never know how to end presentations, so I just whip right through into the discussion and hope no one notices. So.
Didn't notice. So is there anything that's similar to TORCS but for urban environments, so you can try writing a self-driving car AI?
Not that I know of, no. Unfortunately, that would be cool, but not that I'm aware of. Yes. Sorry. Anyone? No, yes, 2. All of a sudden, it's like a bidding war.
Have you looked into the drone stuff, like the Parrot AR for flying equivalents?
No, I really just extended it into the car space because it's cheaper and more manageable to build an actual one if you want it. I mean, some of the drone stuff now, you can actually just buy commercial off-the-shelf radio-controlled quadcopters that will have, you can fly them certainly via iPhone and will have like an open source API. But you can construct your own cars probably more cheaply as well. It's all right, I remember.
So how expensive or is it to put a rangefinder in one of those remote control cars?
Well, one of those remote control cars, I don't know, but a generic, less expensive remote control. A rangefinder will set you back about $20 for a sound-based, an ultrasound-based one, and about that big, and if you have the appropriate framework. So I've got one at home that I never finished building because I didn't realise something really important about how robots work and didn't buy all the parts. So if you're going to get into this, don't buy what I bought, which is like an independent chassis that doesn't do everything. Get yourself something probably called the Polulu, P-O-L-U-L-U. And that is a great base for constructing these things, and you can just mash more parts on it, including rangefinders. So it comes blind, so it doesn't come with a rangefinder, but it comes with 2 wheels, reverse on each. The issue I ran into is I couldn't ever reverse my wheels, so my turning circle was about 100 feet. So if you get one of these little ones, they can, spin on the spot and do all that stuff. And then that'll come with an Arduino on top of it, so you can give it some onboard intelligence and wire it up to a Bluetooth controller to something with a bit more grunt. And then you can stick on about a $20 rangefinder. It's probably not going to be enough just having one rangefinder. You might want a couple of different inputs to correlate as well. And then if you are like ludicrously non-dexterous like me, you also might want conductive glue instead of soldering, which you can which you can purchase from ThinkGeek. But I haven't quite got that far. But certainly my efforts at soldering were not to be repeated. Thanks. Over there.
Sorry, I wasn't sure if I might have missed this, but did you actually get to the stage where you could test your driving bot against the other, I think, C++ or Java implementations?
Yeah, well, yes and no. I never, at no stage did I choose to do so, and I have not done it. But to do it is extremely straightforward. You just add the elements to the configuration and it will happily race the other bots against it. But because I never built a competitive entry, I really just took the baseline. There wasn't really a lot of point. I just would have got totally owned. But yeah, absolutely. That's the next step.
Okay, so you can just straightforwardly just grab a bunch of other bots and just like race them on your machine? Or?
Yeah, absolutely. So I downloaded all of the entries for 2010 and 2011, which are all C++ and Java based. And because I'm running it in a VM on a notebook, it's probably not the right environment. But yeah, absolutely. You can execute each one of them in their own process space. The central server will take care of all of the messaging over the network, and it will simply run it. And so what the actual competition, you submit your bots. I'm sure if we submitted like a Python-based thing that they would go, yeah, sure, I can run that, put it in. And they have 4 parts to their racing year, and they associate them with IEEE conferences. There's a computational intelligence and games special interest group, and so it's quite well organised.
Okay,
yeah.
Thanks.
Cool.
Any other questions? Yep.
Does anyone want to see that 100-mile-an-hour car while I talk still? I kind of want to look at it again. I'll turn my sound off and we can just I'm just going to find it and push play before I answer this question. There we go. I'm just going to leave this in the background. It's just... Right, sorry, your question.
Okay. So I was just wondering, does TORCS have like an input for GPS coordinates or something? Because surely you could base some of your mapping off.
Yes,
an absolute
absolutely.
position
No,
like that.
the lack of a GPS is one of the most baffling non-inclusions of the competition. There is no GPS available to the car.
Oh.
So that's why you go to the effort of mapping in such detail, because the actual tracks are in a standard XML format. You could actually extract the map from that, but the competition has novel maps that you haven't necessarily seen before, so you can't rely on the pre-existence of maps. Plus, it's way cooler to explore the mapping algorithm, because that's what you could use to drive something around a random room, for example. So it depends to what extent you just want to like game the competition versus like build something of your own that's competent in the field. So it depends what you want to use it for.
So is the mapping to, like, you do one lap of the track and then you can figure out kind of a determination of how you're going to turn the corners better the next time round?
Yeah, exactly. Yeah. So not all of them do that. Some of them would do, for example, just look ahead to the distance of their maximum sensor and go, well, I just assume that that's the best path at the end of that sensor, and then plot the closest curve. So that'd be like an example of local planning, because you can see 200 feet or something, because it's a US thing. So because you can see 200 feet, you can plan 200 feet. But if you want to do like a more global state analysis, then you need the mapping. Yep. I don't know how we're going for time. I've stopped paying attention.
Okay. We've got time for a couple more.
5 more minutes. Awesome. Chuck them at me.
Hi there. I was just going to expand on what the other question about the RG pilot and so on, and it's a little bit related to this. Do you have sensors like accelerometers in the simulation? Because the first thing you would do if when anyone's making sort of quadcopter or anything is you get an IMU, so you can actually roughly guess where you are based on accelerometer and compass data. And it just seems a little bit weird if the virtual version wouldn't have the very first sensor that you would buy and stick on your autonomous device. GPS is not particularly reliable, but you definitely have an IMU, so you could guess where you were relative to the start position.
Yeah, well, you do have a few sensors. One is that you have this non-physical sensor, which is distance from the start point. So not the as the crow flies distance, but the proportion of the course that you have completed. So you get that kind of, you get a number of some locating information, but nothing that will give you an absolute coordinate system is in the system whatsoever. Whereas a GPS might, and so the answer to your question is yes, if you're happy with a relative coordinate system and some noise, but
I mean, do you actually get accelerometer values, like forces that are acting on the car? Because like an IMU takes that not positional information and extrapolates a position from it.
No, you don't.
Okay.
Or not as far as I think you just simply don't. You get speed, you get your current velocity, but no acceleration. So you can't quite get it all.
Oh, well, from velocity you can work out your acceleration.
Yeah, yes.
Yeah, you can sort of fudge around. It's just funny that when I'm first thinking about it, I'm going, oh wow, it might actually be easier to make the real thing because you don't actually get enough information out of the virtual system.
Yes, that's very true. Because even for an Arduino bot, you can just buy a GPS little bit for it that's not terribly expensive. I mean, it's not accurate on the scale that you're driving your Arduino bot around generally, unless you're going quite far.
I mean, none of these things like quadcopters rely on GPS like for their only source. It's only for doing waypoints and so on. I was just thinking when you were talking about a rangefinder, of course, a single point rangefinder isn't going to get you very far. The first thing I thought of was, well, strap a Connect on it if you're making something large enough. And actually there's been some chats on the OzHS mailing list in the US. They do this power racing series where they basically overclock kids' ride-on toys. And I think it's something like you start with a ride-on toy, you've got $500 to make it go as fast as you can. In that case, it's actually supposed to be ridden by a human, but it'd be very easy to have, because they're not particularly dangerous. Like, you don't really want to be at a NASCAR race where the cars are being driven by robots unless you're right at the back of the grandstand. But I imagine if it was only a little thing that went about 20 kilometers an hour and there were plenty of tires between you and the car, it would actually be quite fun. And you could easily stick a Connect on something that size and it wouldn't weigh it down so much.
Absolutely. You can buy like these various semi-homebrew systems, especially from the US, where they're things like, like a Connect on some tank wheels with, you can get into it if you're willing to, if you've got the bucks and the interest, you can go quite far with it. And then the GPS sensor just constitutes another piece of probabilistic information about your current location. So you integrate all of these sensors into a probabilistic model. Well, you don't have to, but it's a good way to go. And then, so there's the difference between deterministic and probabilistic. Like this thing's deterministic, it just drives off whatever it's being told at this minute in time. It has no real history other than the map I built up. Whereas probabilistic models go, well, this thing's putting me here with this probability, I've got this conflicting information, I'm going to assume that I'm in this spread of potential locations. And, the math gets, big, but actually a lot of it comes down to some pretty nice, pretty implementable algorithms. So, yeah, sky's the limit.
I think we've got time for one more.
Okay, so you mentioned somewhere here that you were going through various steps, and the last step was to develop a a strategy for approaching the race, which is kind of, in the future. So what are the elements that people have been, how are people approaching that part of it?
Okay, so I'm a relative newcomer to like this specific competition, so I have no idea what people are actually doing. But the kinds of things that I covered in my course and that I'm aware of is one of the most obvious things to do is just calculate the shortest distance or the fastest possible course. So they're not the same thing because you can only corner so fast. But you could pre-calculate through a number of mechanisms what that course might be. So you could do something like dynamic programming, which is that you drive round and round and round and round the course and provide reinforcement learning about what is a quick, a fast or a slow path. Alternatively, you could provide some kind of search. So if you had a model of your motion and of your speed around turns, you could implement a cost model based on the angle of turn and try to calculate using that method, like what the shortest possible course is. It's really the integration of that with the likelihood of hitting an actual physical opponent car, which I think is challenging for this particular competition, especially given the time constraints involved. So one thing you could do is if you took the map that I just produced, you initiate every space in the track to a cost of 0 and the edge to a cost of, oh my God, I've died. You could do something like, and then you could do something like, well, the probability of me being wrong in space is say 20%, so I'm gonna have a 20% buffer from every physical thing. And then you could layer on other things into there. So you could layer on proximity of opponents. And if you got like really ludicrously good at it, you could start to then try and literally place yourself in places that were difficult for your opponents to deal with. So a human driver will do that. They will, prevent cars from taking a final line, and they will drive more slowly than they need to drive just to kind of, annoy the guy behind them or to make it challenging for that. And that kind of thing is way too expensive to calculate in in 2/100ths of a second, obviously. So the architecture for these things, explodes. And again, it depends what you're using it for. Are you gaming the race? Do you want to build your own robot? It's going to come right back to what you're trying to build it for.
Okay, I think that's all we have time for in questions for this session. I'd like to thank Tennessee for his time. Obviously, from the questions, it seems that it was a popular topic.